So the next talk is on MAGMO, mapping the galactic magnetic field through OH masers by Jimi Green, but the talk will be given by Tim Robishaw.
All right. Hey, everyone. Jimmy, unfortunately, wasn't able to make it. Last moment, he was called in to commission a new phased array feed on the Parkes telescope. Jimmy just took a position as the Parkes staff scientist down in Australia. Is the microphone cutting out? All right. Let's see. Is that any better? All right. So I'm part of this project with Jimmy, so as an SOC member, I'll go ahead and give his talk. So OH is a paramagnetic molecule. It's one of those molecules that Tom was talking about, very strong Zeeman splitting. 1665 megahertz transition has the biggest OH Zeeman coefficient, or biggest Zeeman coefficient. It's also one of those rare cases where you can get a full splitting rather than just a partial splitting. We'll see that in a second and why that's important. Okay, so the MAGMO project that we're going to be talking about today, its fundamental aim is to see if hydroxyl masers can be used to map the galactic magnetic field. Okay. Here's Zeeman splitting of an OH maser. OH masers are very nice because they're very narrow compared to most thermal OH lines. They're about 1 kilometers per second. Because of the high Zeeman coefficient, if you have a milligauss strength field in a star formation region, you'll get a complete splitting of the line. If you look at what these OH masers look like towards ultracompact H2 regions, you'll see that the masers are lined up along the periphery of the H2 regions. When you look at them with VLBI and the magnetic fields, these numbers in Jimmy's slide here are a little small, but up here, these color-coded by velocity measurements show that the field direction in each one of those measurements is all aligned. So there's a coherent field direction throughout all these ultracompact H2 regions. Turns out, we'll go back here. How do you do that? There we go. Large-scale magnetic fields have been known via Faraday rotation throughout the entire galaxy. We'll see some nice maps of that after the coffee break. There's a very interesting result that's come out over the last 35 years. That is, one, just a few years ago, is that ultracompact H2 regions in the Milky Way, very large ones, are known to exhibit the magnetic field of the large-scale Milky Way. Another one is that over here, well, we just said that, and that the strengths are very strong, about 1 milligauss. Another one that was discovered in 1974 and has been consistent over the last 30 years is that if you map out the direction of the field in each of these ultracompact H2 regions, they follow the large-scale field all the way across the disk. That's something that just keeps happening every time we point towards one of these masers. It's pretty amazing. Why should this be? Star formation regions, lots of turbulence, lots of dynamic processes. Why is there a memory of the large-scale field? So it could mean that these things play a dominant role, or that magnetic fields play a dominant role in star formation, as Crutcher and Heiles reviewed in 2003 with Tom. Could also mean, potentially, that the fields don't have any strong effect on the process. But for some reason, there's some contraction. During the contraction, somehow the magnetic field comes along with it. Another interesting result comes from Frank Hsu and collaborators, Lee and Hsu. They claim that when you have a collapsing core, you'll retain the direction of the ambient magnetic field. Pretty hard paper to understand, but this is one of the results from that, these two papers. So what's the big idea? We want to go out and measure these towards, or fields towards ultracompact H2 regions. So we used this team here, including Naomi, Ann Mao. Unfortunately, Jim Caswell passed away last year. He was a major player in this project. Jimmy Green here at his Xamon store. And we all went to APCA and tried to measure towards sites of high mass star formation that were selected based on methanol maser emission. We went out and tried to find corresponding OH maser emission in these high massive star formation regions. We were very successful. And then we tried to measure Xamon splitting simultaneously in all of the OH transitions. So these all have strong magnetic fields, or they all should be sensitive to strong magnetic fields because of their Xamon coefficients. So we also used the new back end on the ATCA telescope that allowed us to get very high spectral resolution and got very good sensitivity in this large-scale survey. The results, well, let me tell you about where we pointed. We pointed across a large chunk of the Milky Way seen in the southern hemisphere. I'm going to show you some results from a preliminary reduction of the data. We're still working on the full set. The preliminary reduction is this region in cyan here, and we're looking right down the tangent of the Carina-Sag arm. Okay, and over here, this purple shows in a velocity longitude diagram the star formation regions that were intercepted along that region. So the results are here in the X's, the red X's, are extragalactic rotation measures, positive magnetic fields. So those are galaxies, external galaxies going through all of the ionized, magneto-ionized material in the Milky Way, and we can measure magnetic fields from Faraday rotation. Each one of these green boxes is a pulsar rotation measure. Those are the negative ones. Each of the stars, or the asterisks, is a pulsar with a positive magnetic field. So in general, those X's and stars show there's a positive magnetic field in this region, in this tangent. The Xamon measurements are these yellow crosses. The yellow crosses also show a positive magnetic field. So there's some consistency there. There's a coherent magnetic field in each of these tracers across about 5 kiloparsecs of the spiral arm. There's a problem. That problem is that the magnetic field that is positive in Xamon splitting points away from you sensibly. It's what Doppler shifts do. But in 1972, Dick Manchester decided it was inconvenient to have negative rotation measures correspond to positive magnetic fields, so he changed the convention because he was lazy. So that's a problem, but we're not the only one who's had this problem. In 1896, Xamon measured the Xamon effect, and he said it comes from something called an ion going around atoms, and that ion is positive. Well, it wasn't too long after that the electron was discovered. He was forced to send Lord Kelvin a note saying, well, I'm sorry. In fact, I got the quarter wave plate I was using wrong. It's a negative particle, which came to be known as the electron. It's not the last place we had a problem. Turns out the IEEE has defined right and left circular polarization since 1942 in a particular way. They even put it in their logo. If light is traveling this way, the electric field goes that way. Radio astronomers have always known that. Ever since the first book on radio astronomy, we've been doing this. We're very consistent. But there's a problem. Optical astronomers use the opposite convention. There's another problem, Stokes V. It's an arbitrary definition. Since early times, 1958, 1966, the Bibles of radio astronomy have always used left minus right as Stokes V. So if you were going to reach for one of those Bibles, you'd say it's left minus right. Well, in 1973, it was discovered, well, let's take a step back. Before 1973, Gerrit Verskure, we just heard he discovered the only Zeeman effect in the interstellar medium. And we did that. He measured right minus left. That's okay. Oh, or no, he said left minus right. But he plots right minus left. And there's a note added in proof saying I got the sign wrong. He actually got the sign wrong because he didn't calibrate his left and right circular polarization. So, trouble. 1973, Gart Westerhout said, we got to get on the same page, people. Just like the CMB folks got a note from the IAU back in December. Get on the same page. We have conventions. So they said, IEEE right minus left is Stokes V. Circular polarization also changes upon reflection. So if you have 3 mirrors in between your feet and the sky, you get all those changes. So lots of problems. So here's 1974. Dick Crutcher comes along and says, right minus left. He was right on target. None of these guys ever defined their IEEE, whether they were using IEEE, but we give them the benefit of the doubt. But then Crutcher makes his 1981 non-detections. He doesn't bother to say anything about what Stokes V is. Then Trollin and Heiles and Dick Crutcher make all these other measurements. But you can see that neither are they consistent with each other. They're not consistent with themselves over time about what Stokes V is.
Consistency is the hobgoblin of
So hey guys, what's the definition of Stokes V? I don't know. I mean, I don't know if these guys can agree on anything. They can't even agree with themselves. It just doesn't make any sense. So if you look at all 53 radio Zeeman papers and you look at this, it's bad news. These guys aren't the only ones that have problems. All right, 30% of the time, people define RCP. Then over here, 53% of the time, they're using the correct IAU definition. And then over here, we see, that Stokes V is defined at all only 43% of the time. So that's bad news. Then Jimi and Naomi, Jim Caswell and I had a discussion, well, what if there's a problem with molecular Zeeman splitting? Right? Atomic Zeeman splitting is easy. Electron going around and around. You can figure out which transition should have right and left circular. Molecular, you look at a quantum mechanics book, you start with a Hamiltonian. You have energy transitions, but you don't keep track of which polarization you should see in which transition. So we went through the quantum mechanics, and luckily we found it matches the atomic. That's good. So we're back in this position. What do we know? We also know that we're back where we started. Pulsar measurements have a different sign. State your conventions if you're a polarimetrist. So we'll just leave it here. Here's the survey. We want to figure out, can we use these as a tracer of a large-scale magnetic field? We now have over 100 degrees of longitude. We're reducing the data. We'll have a final release. We'll see, does this reversal happen over a large scale, or is there something wrong with something in the process? But we'll get to the bottom of what's going on, and we'll try to understand, can we use these OH masers as a tracer for the large-scale magnetic field? So I'll leave it there.
Okay, let's have some questions for Tim. Paulo?
Paulo.
So then how do you define Stokes V in the linear phase?
Sorry.
How do you define Stokes V in the linear phase?
I don't understand the question.
How do you define it in the linear basis? Well,
So in the linear basis is IXY minus YX or YX minus XY.
Oh, yeah. Well, I've got a paper about everything you ever want to know about how to define Stokes V. So let's sit down and go over it. It will be of no interest to the people here. Yep.
so just to be clear, your measurements, you had like 5 or 6 measurements, and you say they went in the opposite direction of the rotation measure?
That's right. So they're consistent with one another across 5 kiloparsecs, but they are in the opposite direction in sign from those measured by pulsars and extragalactic sources using Faraday rotation.
And it's not confusion, it's real. You mean real, to take into account all this stuff over there.
Well, that's what the entire, what this could potentially be, a very strange arm. Maybe, you know, there were only a handful of observations over the last 30 years. Maybe by looking at these new dozen sources along the tangent in the SAG arm, that's just one weird place, right? Or maybe there's a consistent problem that we have to uncover. But having the entire 100+ degrees in our survey, we'll be able to get to the bottom of that question. Yes.
Okay, one more question from Enrique.
Going back to assuming there's no confusion.
Yeah.
One question is, how can we know that the physical conditions that are triggering the masers are not altering also the local magnetic field, and that you might be getting like a biased survey of the magnetic field?
Yes, yes. I don't know the answer to that question. That's something that we'll have to work with folks doing simulations on. So that's a very good opportunity to learn something about that once we've got the full set of hundreds of Zeeman measurements to compare with.
It's a nice set of measurements. I'd be shocked if they lined up.
Yeah.
Shocked.
Good.
Okay, thank you, Tim.